Hello. So we're we are to discuss about the second condition for equilibrium. We already discussed about the first condition for equilibrium, which tells us that the net forces acting on an object that is in equilibrium must be equal to zero. Now, the second condition for equilibrium. The second condition for equilibrium will actually focus more on rotating objects or rotational dynamics. A necessary condition for a body to be in rotational equilibrium is the sum of the torques about any point must be zero. So this condition is known as the second condition for equilibrium. For the first condition of equilibrium, the quantity that we are dealing with is the net force. But for the second condition of equilibrium, we'll be dealing with the net torque. And what is torque? So torque is a measure of the force that causes an object to rotate about an axis. So torque is the one that causes an object to rotate about an axis or about its fixed point, or again, we call it as an axis. It can be determined by multiplying the force applied, represented as F, by the perpendicular displacement of its line of action from the pivot point. This perpendicular displacement is called the moment arm or lever arm, represented by R. Therefore, mathematically, we can express torque is equal to force times R. So you have here torque times force times R, or the lever arm. Torque is actually the cross product of force and the lever arm. And we will discuss further on that as we move on in this topic, or as we move on in this lesson. So let's dig deeper into torque as a quantity. So in finding the torque associated with a given force is to resolve the forces into its components, parallel and perpendicular to the axis of rotation. So if you look into the illustration here, we have here the axis of rotation there, and we have here the force that is applied, which is represented by the red arrow. If we think of it, when you exert force on an object and you try to rotate it, what will be the component of the force that actually causes the object to rotate? So the parallel component of that force exerts no torque because its lever arm is zero. So what's the displacement between the point of action of that force and the axis of rotation? So because the lever arm is zero between the axis of rotation and the parallel component of the force, then therefore the parallel component of the force does not exert any torque. But on the other hand, the perpendicular component of the force produces torque. Now, what will be the perpendicular component of the force equal to? Your perpendicular component of the force is equal to F sine theta, which of course theta represents the angle at which your force is exerted. Thus, we can generalize that the magnitude of the torque produced by a force at a distance r from the axis of rotation is given by the mathematical equation torque is equal to the r, or the lever arm, or the distance between your axis of rotation and the point of action for the force, multiplied by the perpendicular component of the force, which is F sine theta. So that's the formula that we can use to solve for torque. So let's have here an example about torque and the second condition of equilibrium. So solve for the resultant torque about points A and C when the forces shown in the figure act on a 5 Newton rod. The rod is 6 meters long and its weight is acting at its center. So we have here a 6 meter long rod from point A to point E, and there are 5 forces acting on the object. You have their point A, which has a force exerted at 2 newtons. You have here force B at 3 newtons, force C at 5 newtons, force D at 4 newtons. For force B, it's exerted at 60 degrees. For your force D, it's exerted at 30 degrees. And for your point E, you have here a 6 Newton force. So what we are asked here is to solve for the total torque. Of course, the resultant torque will be the sum of all of the torques acting on the object. So first, remember that to solve for torque, torque is equal to your lever arm times force sine theta. So to solve for the torque about point A, meaning we consider point A as our axis of rotation. So if A is our axis of rotation, if this is our axis of rotation, then the forces on point B, C, D, and E will be the torques that are acting on point B, C, D, and E will be the one to be factored in whether it causes the object to rotate or not. So to solve for the total torque or the resultant torque in point A, so that will be first, of course, the force that is exerted here at point B, and the distance between the axis of rotation and B is 1.5 meters times. Now, what will be the force acting on that part for point B? That will be actually negative 3.0 newtons sine 60 degrees. Why is it negative 30? Why is it negative? Well, it's negative because your your perpendicular component is going down. Therefore, since it's force, it has the direction, it's fully defined with the direction, so we need to factor in also the direction of that force, which is negative. Plus, now for point C, we have from R, or the value of R will be from the axis of rotation to point C, which is 3 meters, multiplied by the force. So the force is 5, negative 5 newtons, again, because it's going down, or it's moving, or the force is directed towards the opposite direction. Sine, what will be the angle here? Of course, that will be sine 19. Plus, next is the torque exerted at point D, and at point D, the distance or the lever arm is 4.5 meters. 4.5 meters multiplied by the force acting on point D, which is negative 4 newtons sine 30 degrees. Oops, sine 30 degrees. Now for point E, if you look at point E, the force, the 6 Newton force is exerted parallel to the lever arm. And since it's parallel to the lever arm, therefore there is no distance, or the distance between the axis of rotation and the force is 0. So we can just drop the torque acting on point E. So we can leave it. We can leave point E and we can proceed with calculating our values or our total torque for point A. So total torque for point A, you just need to input that in your calculator. So 1.5 times 3, negative 3 sine 60 plus 3 times negative 5 sine 90 plus 4.5 times negative 4 times sine 30. So that will give us a value or the resultant torque at point A, negative 27.9. Remember that well, by the way, the SI unit for torque is Newton meter. So this will be the resultant torque if our axis of rotation is at point A. Now, what does the negative mean here? The total torque about point A is equal to negative 27.9 meter newtons. The negative sign here indicates that the rotation produced by the torque is clockwise. So when we have a negative value for the torque, the rotation that it produces is clockwise. Now, if we have a positive value for torque, the rotation that it will produce is counterclockwise. So take note of that. But we're not done yet. We still have to solve for the torque at point C. So it will be the torque at point C if the axis of rotation is at point C. So now we will need to look into our values again if our axis of rotation is point C. So the total torque acting on the object if the axis of rotation is at point C. So again, we need to add or to solve the resultant torques of all on all points. So for the first one, we have here A, and the distance between the axis of rotation and point A is, you have here we have 3 meters, since each point is 1.5 meters away from each other. So you have 3 meters multiplied by the force, which is, in this case, this will be positive 2 newtons. Why? When you look at the force, when you look at 2 newtons will cause this rod to rotate in a clockwise direction. Since your point, or since your pivot point, or your axis of rotation is at point C, if the force at point A is directed downward, then your rod will rotate in a counterclockwise direction, and therefore that will have a positive value. Remember, if the torque causes it to move clockwise, then that is negative. But if it's counterclockwise, then that's positive. That's why we have here a positive value. Then you have sine 90 degrees plus, next you have at point B. Point B is how far away from the point of axis, that is 1.5 meters, multiplied by the force, which is 3 newtons, still positive because it will cause the rod to move it will cause the rod to move counterclockwise. Then sine 60 degrees plus, of course, we skip point C because it's the axis of rotation. We proceed with point D. And how far is point D from the axis of rotation? It's still 1.5 meters. But however, the force here now will cause the rod to move in a clockwise direction. Therefore, our value will be negative, or our force here will be negative. So that's negative 4 newtons sine 30 degrees. For point E, still, we can actually just leave it out because the force that is exerted on the rod is perpendicular to the lever arm. If you try to imagine that, for example, you are trying to open a door, you're trying to move a door, if your force is parallel to the door, then the door will not move. When it's perpendicular, then the door will move or the door will rotate. So that's the same principle. Now, you can input that in your calculators. So that's 3 times 2 times sine 90 plus 1.5 times 1.5 meters times 3 newtons times sine 60 plus 1.5 times negative 4 times sine 30. So that will give us a value of the total torque, which is at 6.9 meter newton. So the value 6.9 meter newton will be the total torque acting on the rod if the point of axis or the pivot point is at point C. Now, since it's positive, then the rod will rotate in or towards the clockwise direction. So that's for this example. Now, for the next example, you have here a taho vendor carries a 1.5 meter long uh, a taho vendor carries a 1.5 meter long plank on his shoulder. At the ends of the plank are two buckets weighing 40 newtons and 60 newtons respectively. So let's solve for the value of the force exerted by his shoulder, and we just neglect the weight of the platform, or the weight of the plank, because the weight of the plank will also exert a force on the shoulder. And B, where should the taho vendor support the plank for it to be balanced horizontally? So there are two questions. We need to find the value of the force exerted by his shoulder, and where should the taho vendor place his shoulder in between the two buckets in the plank that is supported by the plank for it to be balanced. So how do we solve for the first question here? The first question, we need to solve for the force exerted. Now, what will be the force exerted here? If we look at this illustration, this will be our buckets, your 14 newtons and 16 newtons. That is carried by a 1.5 meter long plank. If our buckets are 16 newtons and 40 newtons, of course, that is the weight of our buckets. We can actually apply here the first condition of equilibrium, since these objects or these forces are directed downward. If it's carried by the taho vendor and it's not falling, therefore there's a force that counteracts this weight to inhibit any acceleration or to maintain that state of motion, which is at rest. So if this is in equilibrium, then therefore we need a force that counteracts these two forces. If these two forces are downward, then we need a force to counteract these two forces downward. Therefore, the force, since we know that it's in equilibrium, then we can conclude that, we can conclude that the net force is equal to 0, and we have the positive force that is unknown minus 40 newtons minus 60 newtons, because these two are directed downward and this is directed upward there. So we need to solve for that force. Therefore, if we move all of these, if we move if we derive an equation for force here, force will be equal to 14 newtons plus 16 newtons. Therefore, the force exerted by the vendor will be 100 newtons. Now for B, we need to identify where should our taho vendor place his shoulder so that the buckets or the plank will neither rotate clockwise or counterclockwise. So let's solve for the distance by which, let's solve for the position by which the taho vendor should place his shoulder. So let x be the distance from the end A. If this is end A, so we will consider this as end A, and the distance between end A to the shoulder of the taho vendor will be x. So let x be the distance from the end of A to the point of support of the shoulder. So we may solve this distance by solve for x by letting end A as the pivot point. So we will consider point A as our pivot point. So therefore, of course, we need to solve for the total torque. If considering point A as our pivot point. Now, what are the forces that are present there? So one, of course, your force that is directed upward, which is exerted by the shoulder. So you know that it's 100 newtons. So it's 100 newtons. But if this is your axis of rotation, remember that we need to identify what direction of rotation will the force cause or will the torque cause. If this is directed upward and this is the point of rotation, then it will cause a clockwise rotation. Therefore, the force is labeled as negative. Sine, since it's just directed upward, so the angle is 90. And we don't know the distance, right? We don't know the distance from point A to the point of the shoulder. So this is for the first torque. Plus, we have here another force, which is we know the distance from the pivot point to this force, which is 1.5 meters times 40 newtons. So that's positive because that force will cause a counterclockwise rotation times sine 90 degrees. So the total torque here is equal to this equation, negative 100 newtons sine 90 times x plus 1.5 times 40 times sine 90 degrees. Now, since this is considered, or we want the system to be in equilibrium, therefore, the total torque acting on A must be equal to 0, since that's the condition for that's the second condition for equilibrium. If this is 0, then we can just replace it as 0 is equal to negative 100 newtons times sine 90 times x plus 1.5 meters times 14 newtons times sine 90 degrees. Now, what will be our equation for x? So, deriving an equation for x, we have here, we just need to transpose this on the other side. That will give us, let us just rewrite this one. Oops. So let's rewrite that one. Let's rewrite that one at 0. So we need to derive an equation. Let's rewrite that one so that we can fit everything. So that's TA is equal to, or that's 0. 0 is equal to negative 100 newtons times sine 90 degrees times x plus 1.5 meters times 40 newtons times sine 90. So what will be x equal to? to derive an equation for x, we will need to take this one and transpose it to the other side. That will give you negative 1.5 meters. Negative 1.5 meter times 14 newtons times sine 90 over y over. So you're left with this expression. To get rid of negative 100 and sine 90, you need to divide both sides by it. So you have negative 100 newtons times sine 90. So that's our solution for x. So inputting that in our calculators, we have negative 1.5 times 40 times sine 90 divided by negative 100 times sine 90. So that will give us a value of 0.6 meters. Therefore, the distance between point A here and the position where the taho vendor should place his shoulder is 0.6 meters, so that the taho vendor could balance the two buckets, and those two buckets or the rod will be in equilibrium, and it will meet the second condition for equilibrium. So that's for the second condition for equilibrium, which is all about torque, or the resultant, or the sum of all of the torques in the system, which should equal to 0. So thank you very much for listening, and see you on our next lesson. Bye.